NASA's Artemis program, aimed at returning humans to the Moon, represents a bold but troubled endeavor. The program's ambition to establish a sustainable lunar presence is inspiring, yet it faces significant hurdles that threaten its long-term viability. At the heart of these challenges is the Space Launch System, a cornerstone of Artemis that has drawn both praise and criticism. The SLS, paired with the Orion spacecraft, is a technological marvel designed to carry astronauts to lunar orbit and beyond. However, its staggering cost estimated at $4.2 billion per launch for the SLS alone and $5.2 billion with Orion raises serious questions about sustainability. As interim NASA Administrator Sean Duffy candidly stated, a lunar program at this price point is untenable, particularly when compared to historical programs like Apollo, which benefited from a much larger share of the national budget, approximately 5% in the 1960s versus less than 0.5% today. The SLS's high costs are compounded by delays and technical issues. The exploration upper stage, a critical component for future Artemis missions, exemplifies these problems. Initially budgeted at $962 million, its development costs have surged to $2.8 billion, with a timeline that has slipped by over 6 years. This cost overrun, highlighted by NASA's Office of Inspector General, has sparked controversy over the agency's ability to manage large-scale projects efficiently. Critics argue that continuing to invest in the EUS, rather than exploring cheaper alternatives, reflects a commitment to legacy systems driven by political pressures rather than pragmatic innovation. For instance, a $9.9 billion amendment introduced by Senator Ted Cruz in the One Big Beautiful Bill, signed into law on July 4th, ensures that Artemis 4 and 5 will rely on the SLS, locking NASA into a costly trajectory despite calls for reform. NASA's transparency about these challenges is a compelling strength. Unlike past programs that sometimes downplayed issues, NASA acknowledges the SLS's limitations and is actively exploring ways to reduce costs. The House version of NASA's 2026 Appropriations Bill directs the agency to evaluate alternatives to the use, focusing on reducing development and production expenses while maintaining the SLS's 130-ton lift capability to low Earth orbit. This directive also tasks NASA with assessing propulsion systems, stage configurations, and commercial collaboration opportunities, signaling a willingness to adapt. However, the decision to stick with SLS for near-term missions remains contentious, as it prioritizes existing infrastructure and political support over potentially more cost-effective commercial options. The Orion spacecraft, another key component, adds to the program's complexity and cost. Its crew module and launch abort system are heavier and less efficient than modern designs, and its ocean splashdown recovery method increases operational expenses compared to land-based alternatives. The European Service Module, provided by the European Space Agency, is underpowered, further limiting Orion's capabilities. These issues are particularly significant given the international stakes. Canceling or delaying Artemis 2 and 3 could damage NASA's reputation as a reliable partner, especially as the European Space Agency has already delivered service modules for these missions. Moreover, the geopolitical urgency to return American astronauts to the Moon before China adds pressure to maintain the current schedule, even if it means relying on an expensive and complex system. The Artemis program's reliance on two distinct transportation systems, SLS, Orion for crew transport to lunar orbit and SpaceX's Starship for lunar landing, further complicates the mission architecture. This dual-system approach increases costs and logistical challenges, as integrating disparate technologies requires precise coordination. While the hardware for Artemis 2 and 3 is nearly complete, the long-term sustainability of this approach is questionable. Duffy's acknowledgement that the current system is too complex to be sustainable underscores the need for a fundamental rethink, setting the stage for exploring commercial alternatives that could reshape lunar exploration. The escalating costs and complexities of NASA's Artemis program have pushed the agency to consider commercial alternatives, with SpaceX's Starship emerging as a particularly compelling option. Starship represents a paradigm shift in space exploration, offering capabilities that dwarf those of the Space Launch System and Orion spacecraft. Its most striking advantage is cost. While an SLS Orion launch costs approximately $5.2 billion, SpaceX estimates that Starship launches could eventually drop to as low as $2 to $3 million, with a more immediate estimate of $40 million per launch. This disparity is staggering. NASA could theoretically fund 130 Starship launches for the price of a single SLS Orion mission. This cost-effectiveness, combined with Starship's reusability and ability to deliver 100 tons of cargo, or 100 people to the moon, makes it a revolutionary prospect for sustainable lunar exploration. Starship's design is another compelling feature. Unlike the SLS, which is expendable, Starship is fully reusable, capable of landing directly on the Moon or Mars and returning to Earth for refurbishment. This eliminates the need for costly recovery operations, like those required for Orion's ocean splashdowns. SpaceX's 2017 proposal, unveiled by Elon Musk at the International Astronautical Congress, envisions Starship handling an entire lunar mission from Earth's surface to the lunar surface and back using a single vehicle. This approach would eliminate the complex orbital rendezvous and docking maneuvers required by Artemis's current architecture, streamlining operations and reducing points of failure. The simplicity and power of this concept make it a bold alternative to NASA's dual-system strategy, which relies on SLS Orion for crew transport and Starship for lunar landings. However, integrating commercial solutions into Artemis is not without controversy. One proposed alternative is using Blue Origin's New Glenn second stage as a replacement for the SLS Exploration upper stage. The GS2, powered by two vacuum-optimized BE3U engines, uses the same liquid hydrogen and oxygen propellants as the use, making it a theoretically viable substitute. In principle, integrating GS2 with the SLS core stage would only require a structural adapter, a seemingly straightforward solution to reduce the EUS's $2.8 billion development cost. Yet, NASA has raised significant concerns. The combined height of the SLS core and GS2 exceeds the clearance of the vertical assembly building doors at Kennedy Space Center, necessitating costly and time-consuming modifications to the facility. Additionally, the BE3U engine's higher thrust could stress the Orion spacecraft structure, potentially requiring a redesign of its solar arrays to withstand increased acceleration forces. Another suggested option, the Centaur V upper stage, faces similar challenges. While it shares technological similarities with the EUS, adapting the SLS core and launch tower to accommodate it would require substantial investment. These technical hurdles highlight a broader controversy: the feasibility of retrofitting commercial components into a system designed around legacy technology. Critics argue that such efforts may only partially address cost issues while introducing new complexities, undermining the goal of a streamlined lunar program. Starship's role as the human landing system for Artemis further underscores its potential and its challenges. The HLS variant, unlike the end-to-end Starship proposed in 2017, is designed solely for lunar orbit-to-surface transport, lacking heat shielding or aerodynamic surfaces for Earth re-entry. It features solar panels and a thermal coating to manage cryogenic propellants, but maintaining and reusing this variant in deep space poses logistical difficulties. Without lunar or orbital infrastructure for complex maintenance tasks like engine replacements, Starship's reusability advantages are limited in this configuration. This contrast between the HLS and the fully reusable Starship vision fuels debate about whether NASA should pivot toward a Starship-centric approach, leveraging its demonstrated ability to perform pinpoint landings and withstand lunar re-entry conditions, as confirmed by laboratory testing of its thermal protection system tiles. The promise of commercial alternatives like Starship and GS2 lies in their ability to reduce costs and increase mission frequency, but their integration into Artemis requires overcoming significant technical and political barriers. As NASA evaluates these options, the potential for a more sustainable lunar program hangs in the balance, setting the stage for broader debates about the future of space exploration. The vision of a sustainable lunar presence hinges on resolving the Artemis program's challenges and embracing innovative solutions like SpaceX's Starship. Starship's potential to revolutionize lunar exploration is undeniable. Its ability to transport 100 people or 100 tons of cargo, land directly on the Moon, and return to Earth for reuse offers a cost-effective, scalable alternative to NASA's current architecture. Unlike the Space Launch System in Orion, which cost $5.2 billion per launch and lack reusability, Starship's estimated $40 million per launch, potentially dropping to $2 to $3 million, could enable frequent missions, transforming the Moon into a hub for scientific research and resource extraction. This compelling vision aligns with SpaceX's 2017 proposal, which outlined a single-vehicle lunar mission, eliminating the need for complex orbital maneuvers. By refueling in Earth orbit, landing on the Moon, and returning directly, Starship could simplify logistics and reduce costs, making sustained exploration feasible even with NASA's limited budget of less than 0.5% of federal spending. However, Starship's adoption as a crewed spacecraft is mired in controversy, primarily due to safety concerns. Unlike the SLS Orion system, which includes a proven launch abort system capable of pulling the crew capsule to safety during a rocket failure, Starship lacks a traditional abort mechanism. While it may offer some abort capabilities, they are less robust, raising questions about its readiness for human missions. NASA's stringent safety standards could require Starship to achieve an unprecedented 100 consecutive successful launches before carrying astronauts, a threshold that reflects the agency's cautious approach but could delay Starship's integration into Artemis. This tension between innovation and safety is a central debate. While Starship's potential is transformative, its unproven reliability compared to legacy systems fuels skepticism among NASA officials and policymakers. The complexity of Artemis's dual-system architecture, relying on SLS Orion for crew transport and Starship for lunar landings, remains a contentious issue. Integrating two vastly different systems increases costs and risks, as highlighted by Interim Administrator Sean Duffy's critique of the program's unsustainable complexity. The hardware for Artemis 2 and 3 is nearly complete, and the European Space Agency's delivery of Orion service modules underscores the international stakes. Canceling these missions could damage NASA's credibility as a global partner, especially as China advances its lunar ambitions. Yet, continuing with SLS Orion risks locking NASA into a costly framework that limits mission frequency. Starship's ability to land on the Moon or Mars and its higher payload capacity offer a path to overcome these limitations, but transitioning to a Starship-centric model would require a bold shift in strategy. Another controversy lies in the maintenance challenges of Starship's human landing system variant, designed solely for lunar orbit-to-surface transport. Unlike the fully reusable Starship, the HLS lacks heat shielding and aerodynamic surfaces, relying on solar panels and a thermal coating to manage propellants. Maintaining this variant in deep space, where infrastructure for engine swaps or inspections is non-existent, is a logistical nightmare. By contrast, a Starship returning to Earth can leverage existing facilities for refurbishment, enhancing its reusability and cost-effectiveness. Laboratory tests confirm that Starship's thermal protection tiles can withstand lunar re-entry, supporting the feasibility of end-to-end missions. However, building the infrastructure and political will to pivot away from SLS Orion remains a hurdle. The geopolitical urgency to outpace China adds pressure to resolve these debates swiftly. Artemis's success is not just about scientific achievement, but also about maintaining EU's leadership in space. Starship's potential to deliver frequent, affordable missions could secure this leadership, but only if NASA embraces its risks. The agency's directive to explore commercial alternatives, such as Blue Origin's GS2 or Centaur V upper stages, reflects a willingness to adapt, but these solutions face technical challenges like VIB height constraints and Orion stress issues. Ultimately, the future of lunar exploration depends on balancing innovation with reliability, cost with ambition, and legacy systems with transformative technologies like Starship.